And this is chapter 6 and 5. We will deal with about the op-amp, operational amplifier. Op-amp, operational amplifier, is looks like here, minus plus or whatever it is. And there are two inputs and one output. We call this is VO and V minus and V plus. When you have op-amp in your circuit, you have to determine some variables like that voltage is V minus, that voltage is V plus, and define this current is I minus, this current is I plus. Then you should write I minus and I plus is 0, and V minus equal to V plus. Then you apply, and here, and no equation, and no equation. And you can solve it here. You should remember that you should not apply no equation here. Why? Because we ignore that point. This is V plus supply, and this is V minus supply. If you consider all 5 pins, then you can use those equation. But actually, to analyze the signal levels, that pin is not important. So to remove the complexity to analysis op-amp, we ignore that things. Because of that, we cannot apply no equation here. So remember, when you have op-amp in your circuit, you should define that variables and write the relationship between here and make a node equation, that point and that point. Based on the 2 node equations, you can solve the other part of the electric circuit, including the op-amp. That's a way how to analyze the op-amp electric circuit. Here we are discussing, we are continue to discuss about the op-amp. We have several very conventional and useful the op-amp design. At first, we will ask about why we call the op-amp is op-amp. Because this analog, the circuit, is proposed to build circuit that perform the mathematical operation. That means plus, minus, and multiply. That's the reason we have the why the op-amp, why the op-amp is used. So we call that is a op-amp is operational the amplifier. For example, we want to operate this calculation. I want to get the x. We have 3 variables, x, y, z. Then I want to calculate x plus 3y minus 2z. You want to get that variables. Then, to calculate in the electric circuit, define that x variable is voltage value. So that voltage is Vx, and y is a voltage value, the Vy, and z is a voltage value, is Vz. And it's here, and that voltage value called Vf. So through the voltage values, we can calculate this operation. So to do that, generally the op-amp is used, so we call that as amplifier is operational amplifier. So op-amp. To use such the mathematical operation, there are some basic blocks to functions that operational mathematical operation. So first thing is inverting amplifier. If you configure the electric circuit based on the op-amp, it's like that, then we call that there is a V input values and that voltage is output values, then the relationship between the V out and V in is VO is minus R1 RF V in. That means if you adding the 1 kilo ohm, then you adding 20 kilo ohm, then VO will be minus 10 kilo, 20 kilo, V in will be minus 2 V in. So if you use R1 is 10 kilo ohm, RF is 20 kilo ohm, then V out is always double of the input variables, input voltages, and inverting. We call that as an inverting amplifier. So here, I try to solve why we get this relationship based on the op-amp analysis. You have op-amp, then at first what should we do? We define the variables. It's V minus and V plus, and this current is I minus, this current is I plus. Then first you have to write what I minus is I plus is 0, and V plus equal to V minus. You should write here. Then you should make a node equation. First, I will use node equation because this is reference. From here, we get the V plus will be 0 volts. The second thing is, this is node equation here. What should we do? I can define the current over here. We'll call this is I1, and because based on the KCL here, because we define IF, then plus I1 minus I minus IF is 0. But I minus is 0. Why? Because the current is going into the op-amp. So this is a 0. So that means I1 is IF. Then what is I1? Because I1 current here, I1 is R1. This is a V in and this is V minus. V in minus V minus. But you know, V plus and V minus is equal, and based on this node equation, V plus is 0. So V minus is 0. So that will be V in. And we calculate the relationship between here. This is V minus, and this is V out, and because this is VF, then V minus equal VF plus, this is V out. And what is VF? VF is a voltage drop caused by RF, so RF IF. So V minus is RF IF plus V0. So V out is V minus minus RF IF, and V minus is 0. So this is 0, and minus RF IF is equal to I1, and I1 is V in divided by R1, V in. So there is minus R1 RF V in. So V out is that relationship. So V out is minus R1 RF V in. So if configured this electric circuit based on the op-amp in this way, then the output is an inverting amplifier. Depending on the variables R1 and RF, you can design the gain of this amplifier. Then this is a non-inverting amplifier. If designed in this way, So you can get the non-inverting. I mean the if input is positive, then output will be positive. Input is negative, and the output will be negative. So here we can solve the at first. How should we do? We define this is a v plus, and this is I plus, and define this is a v minus, and this count is I minus. Then you should write things. What is that? V1 equal to v minus, and I plus I minus is 0. So based on here, you can derive the nodal equation. At first, we'll try to here. And 1 is the first. Based on the equation, v plus is the v in. And we get the variables. And again, this is v minus. But v minus is a variable divided by, because I minus is 0. So v minus will be R1 voltage divided by the V out plus RF R1 V out. So because V1 and V plus and V minus same, so because V plus is V in, so this will be V minus. So we adding here to there. So V in is R1 plus RF R1 VO. So VO is R1 plus RF V in. That will be 1 plus R1 RF V in. So if design the R1 and RF, for such as the design the R1 is 110 kilo ohm, RF is 10 kilo ohm, then VO will be 1 plus 1 V in is 2 V in, for example. So by designing that resistor variables to use this the circuit working as like the non-inverting the amplifier. Then this is a voltage follower. It's very useful circuit. It's very useful circuit. So if you have the buffer, then you will use this circuit very well. Very frequently use the circuit. The voltage named buffer amplifier. This is just for the same variables. I mean same values and input and output. Done here. So because of amp, we define that is a V plus, and this contains I plus, and this is V minus, and this contains I minus. Then what should we do? We should write the relationship. V plus is equal to V minus, and I plus equal to I minus, that will be the 0. Based on this node equation, we got the value, the V in is the same as V plus, because over here we know that V minus, and V minus connecting this over here, so the same node, so we know V out is V minus is V in, therefore V out is V in. Then what should we do? Why we use that circuit? This is very useful circuit. This circuit is used for the connection between two different electric circuits. We will discuss about the reason we use the voltage follower and the very important characteristic of op-amp circuit. Then this is a summing amplifier. Actually, this is inverting the summing amplifier. So you can try to, if you want to add in some variables, then you can use that variable here. Okay, because of this is op-amp, we should define the variables here. This is V plus, and define this quantity is I plus, and this is V minus, and this quantity is I minus. Then we should write V plus will be V minus, and I plus equal to I minus, that should be 0. Okay. Then we need to define some variables. We define, this is its quantity is I1, this quantity is I2, and this quantity is IN, and this quantity is IF. So here you can define, because that node voltage is V minus, so I1 is, this is V1 and this is V minus, so the R1, so I1 flowing through the R1 is V1 minus V minus and R1. The same reason, I2 will be V2 minus V negative and R2. And IN will be Vn minus V negative and Rn. And also we can get the IF, because this is V negative and this is V out. So IF flowing through the RF is V negative minus VO divided by RF. So we can make a node KCL in this to get the node equation here. So based on this node, plus I1 plus I2 plus IN and minus I negative and minus IF will be 0. Well, this is the KCL. So we know that I negative is 0, so this is 0. Therefore, IF is I1 plus I2 plus IN. Then we need to define the VF. What is VF? Based on these relationships, this is I Vn, so V negative is voltage drop here, RF IF plus V out. So V out will be V negative minus RF IF. And we know that V negative here, this is same as V positive. V positive is 0, so this is 0. So V out is minus RF and IF. Then IF can be replaced with this current minus RF I1 plus I2 plus IN. Then we adding these current equations here. Then there will be minus RF. Oh, okay, we need to check it, because I plus is 0, so I minus is 0, so that will be 0, 0, 0. Then R1 V1 plus R2 V2 plus Rn Vn. So we can write minus R1 RF V1 minus L2 RF V2 minus Rn RF Vn. This is a way you can make equations to represent this summing amplifier. So V out is about the summing of the hairs, but the inverting summing here. So for example, you insert the RF here, 10 kilo ohm, and 10 kilo ohm, 10 kilo ohm, 10 kilo ohm. Then V out will be minus V1 minus V2 minus Vm. There's an inverting summing here. This case is non-inverting summing amplifier here. So based on, if you decide the values, these register values here, and here, then you can get V out is the sum of some V1 and V2 and V3. It's not inverting, non-inverting summing amplifier. So I remain for you to analysis based on the OPM analysis. It's not difficult. I recommend you to drive this relationship based on this, the analytic circuit. And this is a difference amplifier. This amplifier is very useful when you design the analog circuit, like filters and other things. So this difference amplifier is amplifying the not one values, but the voltage difference between here and here. So analysis first here. What should we do? We first define some variables. This node voltage is V positive. This node voltage is V negative, and this current is I minus, and this current is I positive. Then you write a relationship. What? V plus equal to V minus, and I plus and I minus is 0. Then to get the relationship, because I positive is 0, so based on this relationship, the V positive is voltage divided by R1 and R2 of V2. R1 plus R2 V2. Then based on here, that will be also the V negative. Then we define this quantity as I1 because I negative is 0, so I1 flow this way here. So because I negative is I positive, so I1 is V1 minus V negative divided by R1. So that is R1 V1 minus R1 V negative here. So R1 plus R2 V2. This is I1. Then the relationship between that point and that point, we get the V negative is voltage drop here, R2 I1 plus V out. So V out is V negative minus R2 I1. Then V0, V out is V negative. V negative is R1 plus R2 V2 minus R2 I1. I1 is here. R1 V1 minus R1 plus R2 V2. So we can simplify this here. R1 plus R2 V2 minus R1 V1 minus R1 plus R2 V2. Then make a simplify here. Then you can get minus R1 V1, then plus R1 plus R2 minus R1 plus R2 square. Oh, this is plus, so this is plus, this is the V2 minus R1 V1 plus R1 plus R2 plus R2 square V2. Then that will be changes R1 plus R2. So here, therefore minus R2 V1 minus V2. This is V out. So their value is proportional to the voltage difference between two inputs here, and using the gain of R1 and R2. So we call this circuit is difference is amplified based on the variables. This is a current to voltage converter. So this is another way. If we use the current source, the voltage, current controlled voltage dependent source, like here, for example, here plus or minus voltages and some current here. Then we define this is IN. Then voltage is some variables 100 and I in. We make this is a dependent voltage source controlled by the current. So that is controlled and implemented in this way. Anyway, we can solve the problems here. So to get here, so we can do that. First, define this is I negative. This is a V negative and this is V positive, and this current is I positive and I negative. So we write the relationship V positive equal to V negative and I positive equal to I negative equal to 0. We should line here. Then based on these node equations, we get the V positive is the same with the 0. Based on here, there will be V negative. So we know V negative is 0. And because I input current from here and I negative is 0, so this can flow to here, in here. And based on these equation or circuits, we get that voltage V negative is voltage drop here, RF, IN, and this voltage V out. So V out will be V negative minus RF, IN. And we know V negative is 0, so V out is minus RF, IN. So this output voltage is proportional to this input current here. So we call that is a current to voltage converter. This is a negative resistance converter. Because we have the resistor here R. Then if current flow here, then that will be R I. This is general relationship, the resistor. So this R value is positive. Even though current going through this direction, then there is a positive voltage and negative voltage here. The voltage difference is in this direction here. But if you want to make if current going to here, then we make a DC voltage. That means the R is negative values because there's a negative resistance. Actually, in passive element, the negative resistance is not impossible. It is impossible. Mean resistance is negative. That means the resistance supply the power. So actually, negative resistance is called of the another name of the power supply, the voltage supply. So anyway, we can design the circuit with op-amp. It looks like a kind of the negative resistance. So you can design here. So you make a circuit in this way, and then we should define the V negative, V positive. This current is I negative. This current is I positive. And we should write V negative is V positive, and I negative and I positive is 0. So you make the relations based on these node equation here, between here and here. Because I negative is 0, so I in current going to here. So this voltage drop is R3 I in, and that voltage is this is V1. We define this VA, and V negative is voltage drop here I3 IN plus VA, and we define the current is IA, and we define this is V positive, so IA is R2 and VA minus V positive. And also, because I plus is 0, therefore RA going to do it here. So IA also positive divided by R1. And R1 is the same with, V positive and V negative. So R1 V negative. Then V negative is here. I3 I in plus VA. And here R2 IA is VA minus V positive. So VA is V positive plus R2 IA in here. So VA is R2 I2 IA plus V positive, and R2 IA is here R1 1 over R1 R3 I in plus VA plus V positive is that R3 I in plus VA. Therefore, this is eliminated. So remain terms, this term is 0. So you rewrite again R1 R2 R3 I in plus VA plus R3 I in is 0. So we rewrite with I in R1 R2 R3 plus R3 IN plus R1 R2 VA is 0. So R1 R2 VA will go minus R1 R2 R3 plus R1 R3 I in. So can be eliminated here. Therefore VA go minus R2 R1 plus R2 R3 I in. So our target is we got the V out here. And what is V out? Actually V out is the same way that V negative. So V out is V negative. And V negative here R3 I in plus VA. And VA here. This is VA. So R3 minus R2 R1 plus R2 R3 I in. There will be minus R2 R1 R3 I in. So V out is the values. So the voltage drop here, I mean, in the viewpoint of the I in, this is like one block here, and block here. Then I in, go in there. This is I in, then voltage drop is some K I in, but that value is negative. The V is Ri, then voltage is negative values. So we call this is negative resistance converter. Here. So we have several examples to use the op-amp for implement some mathematical operation. So this is kind of a basic block to operators. For example, inverter and amplifier and adding or other things. Before the implement the operators based on the building blocks of the inverter and amplifier, we need to know about why we have to use op-amp to do that. To building a block to operational functions, we have another reason you have to use op-amp here. That is a loading effect. We will discuss about loading effect later, but we will simply introduce. I will simply introduce the loading effect at first. Loading effect is the phenomenon between when we combine two different circuits. For example, I design some circuit here. I design circuit 1. So the output of the circuit is VA. We design the circuit A in this way here. And but when you define, for example, I want to make a 5 volt here. I designed the VA 5 volt based on circuit 1. And I want to insert the circuit 2, the 5 volt. So to insert the 5 volt, I use circuit 1. So because the output or circuit 1 is 5 volt, so we combine the two circuits. we expect that the input of circuit 2 is pi volt. But unfortunately, when two circuits is combined in this way, VB is not same with VA. We call this is a loading effect. This is very important problems when you combine two different circuits. I will give you an example over here. For example, we have one simple circuit here, plus minus, for example, 10 volts, and inside here is 1 ohm, this is 9 ohm. So VA is designed to generate 9, 1, 9, 10, 9 volts. So this circuit is designed, the output is 9 volts. So I want to connect, I have some the resistor bank here, the circuit 2. This was 1 ohm, this is 9 ohm. I expect adding here is 9 ohm, 9 volts. So this is circuit 2 and this is a circuit 1. So I insert the 9 volt into this second circuit. So to do that, I combine this circuit to here. So the circuit looks like here, 10 volts. In circuit 1 is 1 ohm and 9 ohm. Then the circuit 2 is 1 ohm and 9 ohm. So we're adding here, then this will be another voltage VB. Then what is the VB? VB is, this is a 1, I mean this is a resistor 1 and this is another resistor here. So there will be 1 plus, this is 10, 9 parallel 10, 9 parallel 10, 10 volts. So there will be 1 plus 9 plus 10, 9, 10, 9 plus 10, 9, 10, 10. There will be 8.257 volts. We expect that voltage will be 9 volts, but based on this effect of the circuit, that voltage changes to the 9.257 volts. So between coupling two circuits, the result is different. We call this is a loading effect. Because of this loading effect, we cannot design the electric circuit as a part of here. We design some circuit 1 and circuit 2. We cannot combine here. Why? Because just connecting two circuits, the performance of A1 and the performance of 2 is different. I mean the performance change by connecting over here. So loading effect is very critical problem. So to prevent this loading effect, generally we use voltage follower. I will give you some example here. We have one circuit 1 is a voltage divider using the V in, and this is 20 kilo ohms and 60 kilo ohms. So based on here, the VA will be 20 kilo, 60 kilo, and 60 kilo V in. Therefore, there is 4 V in. So we adding the load here, 3 kilo ohms. So we expect that I insert this voltage to the load is, we expect that 43 V in. But connecting this circuit, VB is not that values. Because over here VB will be the resistor bank, so VB is 20 kilo plus 60 kilo parallel 30 kilo 60 kilo parallel 30 kilo and V in. So there will be 20 kilo plus 60 kilo plus 30 kilo 60 kilo 30 kilo 60 kilo plus 30 kilo 60 kilo 30 kilo and V in. There will be 1/2 V in. It's just connecting the two different circuits, the output is different. We expect 3/4 V in, but the change is half V in. To prevent here, we can insert the voltage follow in here. Then in the check, what should we do? At first, we define this is V positive and this is V negative. Then this is I plus and this is I minus. Then you know this quantity is 0, so this quantity is 0. So because this quantity is 0, so this VA is 20, 60, 60 V in is 3/4 V in. Based on this voltage follower, the output value over here is also VC is 3/4 V in. That means adding the voltage follower here, we can combine two different circuits directly. Even though the initial design of circuit A and circuit 1 and circuit 2 is not changed. This is a reason why we have to use the voltage follower. Actually, later, maybe the next semester, the circuit theory second, we will discuss about why the loading effect happens in the point of the input impedance and output impedance. We will discuss about that later, maybe next semester, the circuit theory second. And this is another example of the design of the OPM, the circuit here. If you have a mission to design the V out is -5 V in this way here, then the requirement is output voltage is element voltage of 10 kilo ohm resistor. Then output is a negative amplifier V in. Then you can use this circuit. This we already discussed about that values is inverting amplifier. So we already know about that. If we use that circuit, then what should we do? First, this is the V positive, V negative, I plus, I minus. Then we should write V plus equal to V minus. Positive is equal to V negative, and I positive is I negative is 0. Then because node equation over here, V positive is 0 because this is ground. So based on here, V negative is also 0. So we can calculate this current is I1. What is I1? I1 is R1 divided V in minus V negative. But V negative 0, so there will be R1 V in. Because this quantity is 0, so I1 coming to this node, it go out, is what I1. So V out, and we can calculate the relationship, this node and this node. What is that? V negative is voltage drop RF I1 plus V out. So V out will be V negative minus RF I1, and V negative is 0. So this is 0. So V out is minus RF, and I1 is here. R1 V in. Therefore, V out is minus R1 RF V in. So to make minus 5, so we make definitely 5. So R1 RF is 5. That means RF is 5 R1. So if you decide R1 is 10 kilo ohm, then RF is 50 kilo ohm. Then you can make this characteristic here. So we can redraw the circuit here. Minus plus ground here, the output, and this is that values. We define this V in, this is a V out. Then R1 is defined 10 kilo ohm, RF is 50 kilo ohm, then R out is 100 kilo ohm, because there's a requirement of the power. Then this circuit is operating like V out is minus 5 V in. Then you have a question, why we choose 5, 10 kilo ohms, not 10 ohm? How about 10 ohm? Is it possible? It is possible. But if you use 10 ohm here, then what is the current of this device or this current here? I mean, I1, if we choose the 10 ohms, then I1 will be 10 V in, for example 5 volts, then 0.5 ampere following to here. So that current, if this is open, that current go to here. I mean, op-amp support 0.5 ampere. But in generally, the op-amp, like this IC integral circuit, the current has a limited by saturation current. Generally, its current level is less than 10 milliampere. That means when you design this electric circuit, including the op-amp, the current flowing to here is similar less than 10 milliampere. So to do that, the order of the resistor, the consists of the op-amp, should be over the 10 kilo ohms. So we generally use 10 kilo ohm or 100 kilo ohms, just like that. But because we don't have any condition about that, so if we choose 10 ohm, it's okay, it's no problem. Because there's no limitations. But generally, we recommend to use the several kilo ohms resistor when you design the circuit, including the op-amp. This is another example to design the positive, the amplifier. In the same way, then you can use it this way. So what should we do? First, we make V plus and I plus, I positive, V negative, I negative. Then V positive, V negative, and I positive, I negative is 0. So because over here, V positive equal to V in, because this is directly connected to the positive, the pin. So that is V out, V in. And based on this circuit, you can get the relationship between R out and V out and V in. What is that? V in is voltage divider, R1 plus RF, R1, and V out. So V out will be R1, R1 plus RF, V in. So 1 plus R1, RF, V in. So you make a 5 volts. So we design this is 5. Then what should we do? R1, RF is 4. So RF is 4, R1. So if R1 is 10 kilo ohm, then RF will be 40 kilo ohm. This is 10 kilo ohm, this is 40 kilo ohm. Then you can get the right, the proper the design values over here. Then this chapter we will discuss about how to implement the linear algebra equation based on op-amp circuits. This is a procedure for the designing the operational amplifier circuit to implement the algebra equation. Based on the one example, we implement the operational equations. Okay, if you want to calculate this equation, 4x minus 5y and plus 2, which is a constant adding, that result is 0. So if we make a block diagram, these the linear algebraic equations, then you can use that. This is x and multiply 4, and that value is 4x, and y multiply minus 5, then that value is minus 5y, and there's constant 2. So we're adding 3 variables here. That value is g. It is 4x minus 5y plus 2. So to implement with electric circuit, so we can design the variables, these voltages. So G value is expressed with the voltage value Vz, and X is the voltage value is Vx, and Y is Vy. Then our final circuit to function this diagram looks like that. I will later, based on here, this is input values, this is Vx, and this one blah, this is 4, and this is Y, Vy, and this blah is minus 5, minus 5. Then there is 4 Vx, and this is minus Vy, and we adding the 2 values, 2. Then this is adding, this is summing the non-inverting summing. So it's that values and that values and that values sum here. So that is the result is Vz. So using here, we can do that. Okay, the first that we need to implement here 4x. So x and 4x and 4x. We know already the block to implement the non-inverting amplifier. That was here. We defined that is R1 and R2. So we make the 4 Vx. And what should we do? We already know about that. We define that is V positive and V negative, and this is current I positive and I negative. So V positive equal to V negative, I positive, I negative is 0. The base of here, we know V plus equal to V minus, but V plus is Vx and Vx, so this value is Vx. So the current is I1, so I1 is R1 divided by Vx, and R1 following this here. Why? I negative is 0. So this is a V out. So V out is R2 I1 plus Vx. So R1 R2 Vx plus Vx, there will be 1 plus R1 R2 Vx. This is the V out. So to implement it, the 4 can amplify 4. So we should make this is 4. So R2 for R1 should be 3. So if we design R1 is 10 kilo ohm, then R2 should be 3 kilo ohm. So we can make that value is 3 kilo ohm, that value is 10 kilo ohm. This is one block to implement multiply 4. The next is we implemented -5. We have y and make a -5y. So to do that, we can do this. The another things. This is inverting amplifier circuit. This is an inverting amplifier circuit here. So we choose that is R1 and R2. This is the V plus, V minus. This current is I plus. This current is I minus. Then V plus equal to V minus. I plus equal to I minus is 0. So based on this location, we know that V plus is 0. So therefore, V minus is 0. So this is a 0. So we can calculate it. I1 is R1 and Vy and Vy minus 0 is R1 Vy. Because this current is 0, so going to this current going flow here. So what is V out? The V out, I mean the relation between V negative is voltage drop here. R2 I1 plus that values V out. So V out will be V negative minus R2 I1. And we know that V negative is 0, so V out is minus R2 I1. Then I1 is that values. So minus R1 R2 Vy. So we want to make a -5. So we want to make this is -5. Minus R1, R2 is -5. So R2 should be 5, R1. So if you design the R1 is 10 kilo ohm, then R2 is 50 kilo ohm. So this is R1 is 10 kilo ohm. This is 50 kilo ohm. We can design it this way. The next, we make a summation over here. So we already discussed about the non-inverting, the starting circuits. So to do that, we make a circuit in this way here. So I recommend you drive this circuit is why this is the adding, I mean, in non-inverting the summing circuit. So it's quite complicated, but you can do that anyway. You can design that value is 10 kilo ohm. This is 10. This is 10. Then this is 10 kilo ohm. Then this is 30 kilo ohm. Then this is 10 kilo ohm. Then you can make a V out is V1 plus V2 plus V3. You can make it this way. So our final circuit is like there. This is the first circuit we design. We doesn't use. We decide to that 10 kilo ohm. This is 30 kilo ohm. We design here, and we use 10 kilo ohm. This is a 50 kilo ohm, and you design the 10 kilo ohm. This is 10, 10, 10. This is 10. This is 30. This is our design, but the original thing is a textbook suggests that values. So it's not important, but anyway, we should. I mean, if we order is several tens kilo ohms, it's okay when you design, when you use OP amplifier, the IC. So anyway, you can make here. But to do this, what we have to do? We design this block and we design this block and we adding. This is 1. This is multiply 4 and multiply minus 5 and summing, adding. Then to that, we make this block, we design this block and this block and configure to function to as you want. Then you remember we called it the loading effect. When you connect this block and this block, the output and input should not be changing. Then you can combine two different blocks. But are you sure this block connection, there is no loading effect? Yes, there are no loading effect because we're using the op-amp in this way. So to check this, we need to check this point. This will be pointer here. I will give you an example why there are no loading effect here. So I will try to solve that problems here. This is a very simple amplifier, inverting amplifier. Okay. Here, minus, plus, and ground. We make a input, ground, and this is output. Here is RO, R1, and R. Actually, we call this RI, RF, and plus and minus V out. Why it does not have any loading effect? Loading effect is happen when this circuit, I don't know what is that, but connecting to this circuit effect here in this problem, then there will be some loading effect. The basic loading effect can be written here. If we have this voltage source here and one series resistance here, we have 10 volts, this is a 1 ohm. Then there are no connections, then there will be 10 volts. Then if you add in here 1 ohm, then V out will be 1 plus 1, 10, 5 volts. If you adding 9 ohm, then V out will be 1 plus 9, 10, 9 volts. That means these output voltage is depending on these other circuits. That is a loading effect. Then if this is series impedance, I mean there are series impedance here, 10 volts, there is a not 1, 0.21 ohm. This is not, this is a 0.21. Then when connect to this 1 ohm, then what is the V0 is 0.1 plus 1, 1, 10, maybe 10 volts. In this case, V out is 0.1 plus 9, 10. It will be similar to the 10 volts. This means this series impedance is small. The effect between the two circuits, I mean loading effect, is very small. So to reduce or eliminate the loading effect, what should we do? When you design this circuit, this impedance, this series impedance should be 0. Then mean R is 0, that means no loading effect. What is that? This kind of Thevenin resistance here. So you can do this. So if you make this circuit is one voltage source V O C M RTH. This is Thevenin theory. You can replace this circuit in this circuit. Then if RTH is 0, that means this circuit has no loading effect. Then you can connect this circuit in with any other circuits. So to do that, to check that this is no loading effect or not, we use the same things. Then what should we do at first? At first, we need to get the VOC. What is VOC? They have voltage here. We already do that. What is VOC? VOC is minus R1 RF V in. Then to get the R Thevenin resistance, we need to check the I short circuit current. We make this current here. We make a short circuit. Then we need to check. We need to analyze this circuit again. This source, and here this is R1. This is amplifier minus plus, and here RI RF. This is up. This is RO, and we make a source circuit here and define this is ISC. Actually, this is not important here. Anyway, this is a V in. Then based on this op-amp, this is a V positive, V negative, this current I negative, I positive, then V plus, V minus, and V positive is V negative, and I positive equal to I negative is 0. Then based on this node, we know that point positive is ground 0. Therefore, V negative is 0. So their value is 0. So this current is I1 is RI V in. Then based on these relationships, we can check the current over here. So voltage drop. So the V out is no V out. No V negative is voltage drop here. RF I1 plus V out. So V out is V negative minus RF I1. But V negative is 0, so we don't care about that. So there will be minus RI RF V in. So V out is minus RI RF V in. But between two here, there will be some resistor here R. Then ISC will be R V out. This is 0 minus 0. That means R V out. Then we make a source circuit. That means what is R? R is 0. So that means V out divided by 0. That means infinite. So in this case, ISC is infinite values. Short circuit current is infinite in this circuit. So what is RT? TH is ISC VOC. And VOC is minus RI RF VN, and ISC is infinite. So what is that? That is a 0. So series resistance of Thevenin theory, Thevenin equivalent circuit, RT is 0. That means there is 0. because series less than 0, that means there are no loading effect. So this circuit has no loading effect. So we can add in the circuit with other circuits without any loading effect. About the related to the loading effect, we will deal with in the next semester in circuit theory second, in the more the practical and more the theoretically we'll derive the effect of the loading effect and how to reduce the loading effect, and how to design the systems when you divide the electric circuit